Okay, so welcome back to class. We'll see if this actually works. I'm guessing it won't, but you never know. Okay. Heard a funny noise. All right, so my apologies to the internet people. Apparently the audio, this microphone is not actually doing anything, which is weird because the camera thinks it is, so there's something going on. But we'll see if my phone manages to capture audio or not, and if it doesn't, then that's too bad because we already told you guys that it's your responsibility to go to class. So let's see here. In terms of course announcements and things, I don't think there's anything special. There's just one more homework to do, and then your final project. On the homework, Karthik was in my office hours yesterday. We noticed that there's some headaches involving installing this Manoff package. So if you get some funny error message, you should contact him, and he'll tell you how to fix it. And maybe give you a hint on your homework while he's at it. He's a nice guy. Any questions about procedural stuff for the course? It's pretty straightforward, I think. This is it for your homework, and then we're done with your homework. Right, so let's see. In terms of course organization, all that kind of stuff, I think that's everything I have in mind. In terms of where we're going in this course, so the last part of this class is a little bit more of a grab bag of different topics, as with usually happens in differential geometry courses. You start with this very coherent picture, and then sadly the field kind of gets very broad, so we have to kind of select out some interesting areas. So today we're going to be talking about vector fields, which is a topic that is close to my heart, because we work on it a little bit. We'll spend today talking about vector field theory, and then next time we'll talk a little bit about vector field discretization. I noticed that conflicts a bit with the class calendar, so I'll update that. But rather than trying to jam 2 lectures on vector fields into one, that felt like the right thing to do. And that way, maybe for fun, like last time I collected some stuff on these normalizing flows, which are an interesting application of vector field in the machine learning setting, so maybe we'll cover a bit of that while we're at it. But for today, we're just going to talk about theory again. Continue with the usual ping pong we have in this course between theory and practice. Before starting, I should credit that a lot of the material for today's lecture is borrowed from a course at SIGGRAPH. The really nice thing about the computer graphics community is they go out of their way to visualize stuff. So even though vector fields are broadly applicable in and out of graphics, the reality is these folks have done the best job of just illustrating what all these notions are. In addition to that, there's a really nice survey that I wanted to point out. This is a state-of-the-art report from a couple of years ago. Well, in my mind, it's a couple of years ago, but I guess all of you guys were in middle school on vector field, and they call it directional field processing, and that's because there's a slight generalization of vector fields, so tuples of k vectors at a point, and how to process these things. At this point, there's been some more work that's continued kind of beyond the stuff that's mentioned in the survey, of course, because it's 5-6 years ago. But even so, it's sort of a good starting point for the introduction to the theory in this space, at least in low dimension, and some nice visualization and all that good stuff. Okay, so we've already encountered some vector fields in the math that we've done in this course, but we haven't really thought about them as their own objects, right? So essentially in today's class, that's going to be our focus, is what does it mean to design a vector field, process it, understand its structure, and so on. So basically, instead of just talking about shapes and understanding shapes, now we're talking about shapes with little directions painted onto them at every point. Right? And we've encountered vector fields in many different applications. I don't think it's difficult to justify why we care about vector fields. To give a few examples, of course, here's some in computer graphics. We use vector fields for a lot of different tasks. Everything from designing interesting textures on surfaces. Amazingly, this old video is from 2007, which is pretty early in this particular literature, and already they have some pretty nice results. Literally putting hair on 3D surfaces is a reasonable vector field application. It also gets used a lot in meshing. So a lot of times there are algorithms that take in a triangulated surface and they want to output something like this object here. I don't know if you can see from the back of the classroom, but this is called a quad mesh for obvious reasons. It's covered in little quad patches. And essentially, if you take sort of an infinitesimal limit as the edge lengths of this quad mesh go down to 0, what you get out is one of these directional field objects. You get a little plus sign sitting in the tangent space at every point on your surface. And so a lot of algorithms for quad meshing will input maybe a triangle mesh of the surface, because those are easier to obtain. And then they'll optimize for a directional field on the surface, which is going to kind of guide the placement of the mesh kind of via the streamlines of the field. Right? And so that's sort of one basic technique for doing meshing. It has a very long history in this domain. And in fact, actually, it even generalizes to volumes. So if you really want to mess with your brain, you can try to think of the sort of 3D analog of quad meshing, which is something called hexahedral remeshing, where you have a volume and now you're filling it with little cube-like elements that can deform a bit. And those plus signs become little, like jacks? Is that what you call those things? You remember those old toys? So they're like 3D plus signs. And creating smooth fields of those is an open challenge, and it's even harder to make them integrable and so on. This is one of these problems that feels like I can just bump up from 2D to 3D, but actually all the 2D quad meshing algorithms just fall apart for really subtle reasons. Vector fields show up all over the place in biological sciences and imaging. There are all kinds of super cool studies in medical physics where like you're trying to understand blood flow and dynamics inside of your body. And of course, anytime you have flows and you encounter vector fields. And you know, this is, of course, applicable to simulation more broadly. And indeed, all the different vector field representations, derivatives, and so on that we'll talk about in this course are directly applicable in the simulation setting. I mean, it's exactly the same formulas that get used in physics, and many of them are attached to different physical systems. Vector fields at the macro scale show up in weather modeling. There's some pretty cool data sets out there where like you have some buoys floating around in the ocean and you're trying to figure out like where the interesting weather phenomena are, like where's the wind circulating around, these kinds of problems. Back in computer graphics, another place where they get used is in vectorization. So like here's a fun paper where like you've got this elephant walking dude here, and you'd like to convert it into a bunch of smooth curves, right? Because this is just a scan of some hand-sketched image. So a very typical approach is to first compute a little tiny frame field. You can see like this is a zoom in on his hat, I think, which is kind of trying to figure out where the pen stroke is moving as you drew this shape. And then you basically use the flows of this to vectorize your image. So like that's the green curves here. And then the nice thing, of course, is that you can zoom in infinitely close to the green guy and it will remain smooth looking, whereas if you zoom in infinitely close to the sketch here, it starts to look like pixels. Right? So vectorization is one of these interesting tasks. Incidentally, for those of you who are computer vision and machine learning students, I would argue this is largely unsolved in that space. I mean, there are a lot of research papers that tackle precisely this, right? Like, it somehow feels like a good machine learning problem to input, an image on a pixel grid and output a set of curves that approximate it. And indeed, there are many papers that attempt this, but I don't think most of them are usable or distributable in the artistic setting. That like they don't really reach that final level of quality. So if you're looking for a good research problem, it's here. Vector fields, of course, show up in simulation and engineering. Anytime you have divergences, flows, velocities, all that, for a fluid is nothing more than a vector field. And all of the same decisions and discretization issues that we'll talk about in the context of geometry in this course also show up in simulation, right? It's exactly the same headaches there. Vector fields these days also show up in high dimension, and there's some really cool modern research that uses it, for example, for generative modeling. So for example, let's say that I have samples that are drawn from some probability distribution. These are the pictures that I was shown in the paper, but really the application is like, generating photographs or something like that. So one thing that you might do is when you're trying to train your generative model, one very simple model for how to do that, because you need some way to basically parameterize the set of probability distributions, right? Like some way to randomly generate a photograph. One thing you can do would be to randomly draw a Gaussian random variable centered at the origin, and then the object that you learn is a vector field that you flow that Gaussian random variable along the field, and it reshapes that Gaussian into a more interesting probability measure. Right, so like here are assorted stress tests for that kind of strategy. Sometimes this is called continuous normalizing flow. So you can see they've reshaped Gaussians into all kinds of weird probability measures here. Of course, these are just kind of fun 2D toy examples. The reality is the high dimensional examples are the one that's more fun and interesting. And indeed, for a lot of generative modeling tasks, there's good reason to use this kind of machinery because it gives you some access to both the density function and the sampling machinery for your probability measure, which is hard to do with some parameterizations. And of course, in our research group, we like them because we can use them for food. So the machinery that we'll talk about today is directly applicable to making interesting weaves on your pies. In particular, I challenge all of you guys to go home and make pies with interesting singular points. bonus points if you can do it with like pairs of singularities that cancel each other out, which I tried to do on a pi and it was like remarkably challenging. So at least for a long time in our group, every Thanksgiving, people were making these interesting topological pies. Over the last year or two, that it's yet another victim of the pandemic. But hopefully we can pick it up again this year. Okay, so talking about vector fields on surfaces is really annoying. I mean, like from my perspective, this is a lecture that I dread giving because it's really formal and annoying to get this stuff right. And essentially, I think when you crack open a lot of modern differential geometry books, you'll notice that suddenly you get to the vector field chapter, which is not too far from the beginning. This is a very basic construction. Suddenly, like the number of illustrations kind of starts to decrease a little bit because we don't like it's hard to think about a lot of the constructions, and moreover, some of the theory gets a little abstract. So actually, when I was preparing this stuff, I spent a lot of time just staring at pictures and doing stupid calculations in Euclidean space to get some idea of what's going on with some of the things that you usually see in like Riemannian geometry in a totally abstract setting, right? Like when you start talking about connections and differential forms and so on, then somehow, especially I would argue in like the last 50, 100 years, the trend in geometry has been to move away from drawing pictures and to move toward doing algebra. There's good reason for that if you're a mathematician, because you can be much more confident that if your theorem type checks, then it's like correct. But on the other hand, what gets lost sometimes is like, these calculations really are trying to do something geometric in nature, and so sometimes that gets lost a little bit in the formal theory. So in this class, since we're not equipped to do a lot of those really scary calculations, I went back and tried to draw some pictures and understand a bit. For example, the different notions of what it means to differentiate a vector field, which I feel like get all glued together in the typical geometry books. Anyway, that's my soapbox. So when we talk about vector fields, there are all kinds of different questions we can ask. The main one that we'll try to answer today is the very first one on this list, which is like, what does it mean to take a derivative of a vector field? And we'll see that that feels like an easy question. Like they have x, y, z components. We could differentiate all those and get some kind of derivative. The only problem is that derivative doesn't make any sense. And so we'll have to go back and kind of fill in some detail to understand, like if I've got a tangent field on a curved surface. Remember, like on your homework, you've worked with notions like parallel transport. So somehow we know that there's a problem when you're comparing vectors on different tangent planes, which is exactly what you need to do when you're differentiating, right? Which is annoying. So that's the thing that we're going to have to think about. And what we'll see is there's a whole decision tree that happens when you talk about defining a derivative of a vector field. In fact, there's no canonical one on a surface or any other manifold. If you take an advanced geometry class, in some sense, this is the very first thing you'll construct. They call it a connection, right? But in any event, beyond that, of course, there are many representations of vector fields. In this class, we're perfectly happy to have coordinates, but eventually maybe you don't. Maybe you never want to see things that don't live in the tangent plane, like the universe outside the tangent plane just doesn't exist. In which case, you have to think a little bit about even mathematically, what is this object we're working with. We'll talk a little bit about vector field singularities and flow lines. So singularities are like points that a field might circulate around in 2D. And defining those and working with them and understanding their topology is a really critical piece of the theory of differential geometry, and really beautiful kind of corner of this area of math. In case all this headache wasn't enough, making it work on a triangulated surface or even just using a neural network or whatever is itself a giant challenge. There's representational issues, how to compute these derivatives. If you work with a neural network, then finding singularities is going to be really a problem in your vector fields. There's no shortage of challenges in this space, discrete and smooth. And I think that explains why, if you look at geometry community, there's such a huge literature of papers that are all on computing and working with these objects, and there's very little consensus on how to do so. So we're just going to give you kind of a quick overview on the sort of theory and discretization of vector fields that you're equipped to read research papers in this domain, and then invent your own vector field discretization, because there's no, we're not done. There's plenty to do here. Okay. So in today's lecture, we're going to focus on the left column, which is mostly just a little kind of toe dip into why I don't want to say that we're going to cover much of the theory of vector fields as much as just to suggest why that theory is non-trivial and some of the basic constructions that are in that space, so that what I want you guys to be able to do by the end of this course is to open research papers, textbooks in this space, and at least understand the statements of the theorems, not necessarily the proofs, like what is this thing telling me about life and why is it important? And I think especially for vector fields, that's a bit of a challenge. So we're going to be drawing some pictures and kind of understanding like, what are all these objects that we're working with, and why should we care? All right, have I done a good enough job, like, downplaying the rigor and content of today's lecture? I'm trying. I'm scared of you guys because I know you're going to hold me to account, and this is a topic I'm afraid of. Okay, fantastic. All right. So, as always, we'll recall a few basic notions, and then we'll dive into some content here. I'm going to have my coffee. They gave me a free cookie today. It was a big day for me. Okay, so right. So here's a surface. I think at this point we have defined and worked with tangent planes any number of times. But of course, a vector field is nothing more than essentially an assignment of a vector in the tangent plane to our surface, at every single point. Part of today's lecture will be applicable to higher dimensional manifolds, and then part will not. Like when we talk about vector field topology, that's mostly a 2D thing for our purposes, whereas like the basic definitions of derivatives and so on will generalize. Now, there's kind of a problem, even just talking about vector fields. Like we like to think of vector fields as functions, right? It's a function that maps points to, vectors. But the problem is that like if, in this class we use a lot of this, like notation, like f maps from, it's moving, from x to y, like that. And there's a bit of a problem when we talk about vector fields, which is like, what is the y, right? Because like somehow you have a different tangent plane at every point. So like it's hard to encapsulate in this notation precisely, like what is the space of vector fields. This is the thing that like you don't have to get too caught up in your elementary differential geometry class. It's perfectly fine to say like, well, it's a map from X to like vectors in R3 with the property that they're tangent to the surface. But somehow that feels clunky, right? And so differential geometers have invented, in an effort to make students as confused as possible, new and fancier notation that encapsulates this notion and generalizes in nice ways. In particular, the object that tends to get worked with in this space, this is the first time we'll see the B word in this course. Namely, we will work with an object called the tangent bundle to our manifold, which is this kind of funny like product object. And the really kind of funny thing about this is that, of course, it is itself a manifold. But the way to think about tangent bundle, notice that typically when we talk about tangent plane to our surface, we have this notation like T, P of M, something like that, right? Like the tangent plane at P of M. The tangent bundle is this funny object, which is the set of all pairs of P and V, where V is in the tangent plane of P, right? And so a very typical way, kind of mathematically, to think about a vector field is to think of it as a mapping from our manifold into the tangent bundle with the property that, what was I going to say? Oh, yeah, with the property that the first coordinate is just your points again, right? And this is kind of a nice notion because it generalizes cleanly, and if you were working in a coordinate-free universe, this object is still something you can work with, but of course then you don't have our sort of basic notion of tangent plane anymore, right? There's no more plane. It's just sort of like an abstract way to glue a plane onto every point on a surface. Incidentally, this is sort of this bundle is one of many bundles that you will encounter should you go into fancy pants differential geometry beyond this course. For example, a very typical thing to do might be to sit at every point on a surface, and rather than attach a vector, right, that's a vector field, maybe you just attach a direction, like a unit vector. So in that case, if you think about it, the fiber sitting over every P, by the way, that's the terminology here, so like the fiber over P in this case is the tangent plane. In that case, the fiber over a point might be like a circle, right? Like the set of all directions rather than the set of all vectors, right? So tangent bundle, in general, the idea of a bundle is to just like attach a thing to every point on a manifold. That makes sense? I think for once, this terminology makes sense. Like bundle is the right word here, right? You're bundling on a tangent vector at every point on your manifold. This is better than like, depending on how quickly I talk in this class, eventually we might talk about like exact and co-exact fields. And that's one of these ones where I can never remember which of those is which, because to me, exact is like a meaningless word in this space. But I digress. Okay. I don't know what a function is. I got when I was preparing these slides, I got a little too ambitious, including some review. And then, of course, we've talked about differentials and gradients of functions. And a gradient is nothing more than the sort of dual of the differential, right? Like the vector with which the differential is taking the dot product, I think is sort of what we showed. Okay. So those are all the ingredients we're going to need for today's recipe. We good so far? Any questions, reviews, thoughts, comments, concerns? Favorite color? Good composers? No? Okay. Right, so here's the basic question we're going to try to answer today, which is how do I differentiate a vector field? And this feels like this is like one of these things where it doesn't feel that hard, and then you try it and you realize like, oh, this is really ugly. And moreover, it's not obvious how to do it. Like there's actually more than one thing here. This is one of these little pieces of theory that is going to depend a lot on your application. That what we're going to see is that there are multiple derivatives of vector fields, and it's not like you can like rank them on a hot or not, like for best versus worst kind of scale here. Like they're just useful in different applications. Some of them appear in physics, some appear in differential geometry. Some, if you're like in 3D modeling, then you do get a choice, and you can at least try to understand that like different choices of derivatives lead to different qualitative behavior in your model. Right? This is one of these, to me, this is the worst part of differential geometry, and so like, I'm just going to warn you, like this is a common point of confusion. In fact, going around my own research lab, I always bug my students to like help me draw pictures of a lot of the notions in this class, and we all sit there at my board every year and get it wrong. This is tricky stuff. This year, yeah, my student David, who used to TA this class, was kind enough to help me with that. Okay, so when it comes to differentiating vector fields, I mean, the short answer here is that it's complicated. There's many different ways to do it, and we have to be quite careful when we go back to sort of the basic definition of what does it mean to differentiate anything, and kind of look at the component pieces. We kind of hinted at this in our lecture on manifold optimization. Remember, like when we talked about gradient descent, we needed to say like, well, first of all, we need a notion of gradient. Second, we need a notion of descent, right? And both of those had to get adjusted a little bit to do it on a manifold. There's sort of a similar picture here, right? Like, if you look at the definition of derivative, it's like the limit as you subtract two things, right? And so we have to decide, like, what does it mean to subtract? You know, how do you take a limit? Like, we're on this curved domain, we can't see off of the surface, and so that's why things are so complicated. Or to put it differently, the basic issue is that you need to identify and figure out how to compare tangent spaces, right? And this is a theme in this course, right? This comes up many times, come up on your homework, previous lectures, and so on. So, unfortunately for us, there are many notions of derivative. Here are three. One is the differential of a covector. So if I compute a differential form, that would be like the df corresponding to the gradient. Then there's one piece of machinery for differentiating those objects. There's something called the Lie derivative, something called the covariant derivative, and we're mainly going to focus on these two in today's lecture. This semester of 6838, or whatever the course number is going a little slower than the past, which is good. You guys are asking more questions in lecture than are typical. Because of that, we may not get to the first one, which involves some differential form, but we'll see if we do. Okay, so I think I've repeated myself about 85 different times on like the reasons why vector fields are annoying to work with and differentiate. So now let's go into a little more detail. Whoops. In particular, here's the basic formula that we're going to worry about. So here, this is sort of our generic notation for differentiating. So we have a vector field x and another vector field y. And presumably, the object we'd like to produce is a third vector field, which is sort of like the derivative of y in the x direction. Does that make sense? That's the object that we're after. And now, if we go back to like college calculus, and we did this in the plane or like in Rn, so we can like freely at liberty subtract and add vectors, we can displace things and so on, and all of that's fine. This is probably the formula we use on the right hand side. But now let's think about what it'll take to make this formula work on a curved manifold, mostly a surface today. So all right, so here's our basic task. Is what we kind of want, in some sense, we have the derivative of, we wanted like this, and we kind of think, well, maybe we can take some limit as t goes to 0 of y. Maybe this is evaluated at p. So, like, what would it mean to take a directional derivative? Well, it's in the x direction, so maybe I take p and add a little bit of x to it, minus y of p divided by t. Right? That's the sort of basic definition of derivative. But there's sort of two issues here. Let's see if we can identify them. So first of all, there's this plus sign here, right? What's the problem with this plus sign? So I've taken a point P and I've added a little multiple of my vector. Yeah.
It'll take you off
Yeah, that's right. So I've got my curve, my donut here. I've got some tangent plane at P. I've got a vector. Obviously, if I displace this far enough along the vector, I just leave the surface altogether. And I don't even have a vector field at that point, so that's already problematic. Right? So this is issue number 1, or letter A maybe, which is that this leaves the manifold. Okay? But we kind of have some machinery for fixing this, like we talked about some in our previous lecture, right? Like we could replace this plus sign with like a flow of some sort. But even if we do that, there's a second issue, which feels like a little bit less of an issue in this class because everything that we do is embedded, but especially when it's not, this becomes problematic, which is the following. So y of P is a vector field of P, which means in particular that it's in the tangent plane at P, right? So there's like a little plane sitting on the surface, which is where y lives. Y at P plus Tx, well, P plus Tx, or whatever our analogy of P plus Tx is, right? I move somewhere else on the surface. Well, okay, so that's some other tangent plane. And so in some very fundamental fashion, these are two very different objects, right? One is in one tangent plane, one's in the other. And we need to come up with a mechanism for comparing them, right? So issue number B here is going to be this, that essentially what we need is like some way to deal with the fact that these are different vector spaces. That makes sense? Okay, so these are going to be our basic headaches in this lecture today. So I think issue A here is somehow, like we have, given actually all the way starting back in like lecture 2 or 3 of this course, we have like kind of a standard strategy in differential geometry for dealing with that, right? So in particular, what we can do, remember, so the basic issue here is what does it mean to displace along x like this? Well, x is conveniently is a vector field, right? So I might as well just kind of integrate along it. So in particular, I could do the following. I could use some curve, gamma p of t. It only really needs to exist kind of infinitesimally, like that. Hopefully we're getting used to this. This is just notation for like a little piece of spaghetti sitting on top of p. And what are we going to need? We're going to need, well, gamma p of 0 is start at p. Gamma p prime of 0 is going to be x of p, right? Because we're differentiating in the x direction, right? And so that kind of suggests that if we take this limit here and we rewrite it a tiny bit, then maybe the object we should be studying is the following. I'm going to write, like already we've decided this expression doesn't make sense. I'm going to write another expression that doesn't make sense, but makes a little more sense. So in particular, we're going to do y, but instead of p plus tx, maybe I do gamma p of t minus y of p divided by t. Does that make sense? So now, at least we've solved issue A, right? Now, if we choose to use this strategy, and we'll see that this strategy actually will suffice for both derivatives we'll define today. Notice that we need to check something. What's the property we need to check? That's right. If I choose some other gamma that also agrees with my field at time 0, I better get the same quantity. That makes sense? So we have to be a little careful about that. In fact, this isn't the only option. We'll see when we talk about the Lie derivative. We'll make a very specific choice of gamma, and then I think later on you could argue that other gammas might work, but really there's one that makes it convenient. Okay, so that's issue number 2. Number 1. Number 2, we're going to kind of, we're all computer scientists here, so we're going to encapsulate a little bit. You need some kind of machinery for comparing vector fields. So here's what we're going to do. We're going to kind of think of our derivative definition as being parametrized by the choice of how we solve problem B. So in particular, here's what we need. We need like, I called it a mechanism in my notes. By the way, this is not the standard notion in differential geometry because they usually just axiomatically define a covariant derivative, but I think that's ugly, so we're going to do it this way. And we can call it the following, which is maybe gamma t p. And here's what it's going to do. It's going to take in the tangent plane, points in the tangent plane, like that, right? So this is kind of like, points in the plane over here. And it's going to do a map from that to t p. Okay? Because once they're in the same tangent plane, then the minus sign makes sense. Does that make sense? I can subtract things so long as they're in the same tangent plane. So I'm just going to, for now, encapsulate and say that, like, I'll define some function that just gives me that map. And then if I choose such a function, now I can finally define a derivative that makes sense. So we're going to write down our expression, and then we're going to agree that it's kosher here. So in particular, notice that the problematic guy in some sense is this one, right? That's the vector that lives in the wrong space. So we're going to do phi t p of y of gamma p of t minus y of p all divided by t. This makes sense? So let's think about what's going on in this formula for just a minute. So like, again, our goal here is to take a field y and differentiate it in the x direction. I'm going to confuse these two things, so I'll just keep repeating that phrase. So what does that mean? That means I need to like scoot a little along x, pick up a y, bring it back, and then compare it to the y where I started, and then and divide by t. Yeah? And so essentially, the two pieces we have here, the gamma and the phi, are taking care of those two pieces. Like, where do I look? Like, where do I pick up the y? And then how do I drag it back? Does that make sense? Yes?
Phi should also depend on x, right?
Phi should also depend on x. Yeah, it sort of does implicitly because it depends on gamma. Yeah.
But even as a function, right? The way you
Not necessarily. So it's an interesting intuition. Can you think of an example that doesn't? I can think of one for your homework. Parallel transport. So parallel transport depends on the shape of the curve, but it doesn't depend on the field. Yeah. It just takes a vector over here and moves it to a vector over there. The stuff that happens in between is irrelevant. Yeah.
But it also depends on where you end up, right?
That's right. So that's all encoded in gamma, right? Gamma has endpoints. Yeah. Cool. Any other questions? This is an annoying notion, so I'm like purposefully taking it kind of slow because this is a thing that's hard to get right. Okay, so we all agree that this is like somehow a reasonable definition. I've made vector space calculations that make sense because now everything's in the same plane. Okay. So this is kind of fun because like now I can make like I can play a fun mix and match game where I just like cook up different phis and gammas and then I get different derivatives, right? And it's kind of funny to think about because somehow it feels like there should be a canonical choice, but it turns out that's actually just not the case. There are just different derivatives that show up in different places, and that's just life in the city. So we'll define the two most common ones. We're not going to derive a bunch of algebraic properties of the two, which is really what you should do if you had like 3 more lectures in this course. But we'll see that at least geometrically they make some sense, and they're reasonable to define, especially in the extrinsic case where like you're allowed to work with vectors that leave the plane. In differential geometry, it gets a little more annoying.
Here's what I found.
The 4 rules of travel. Okay. So let me. All the chalk is like little tiny stuff. Playing that terrible physics class before. Okay, so now we're going to go through 2 examples of what it might mean to differentiate a vector field. We're going to do them on the board first, and then we'll go through some slides that have pictures of what they are. But I want to do the board first because that's sort of band limited in terms of writing speed. Okay, so the first derivative is LIE. How do we pronounce this? Yes, Marcel.
Lee.
Lee. Thank you. If you call it the Lie derivative, then you get a 0 in your next one. Okay, so similarly,
Euler.
Trolls in this class. Okay, so Right. So the Lie derivative is this kind of weird object. It actually doesn't depend on geometry at all. It's purely topological, which is a little funny. Meaning if you like take your surface and you kind of deform it and you deform the vector field with it, the Lie derivative will remain unchanged. That's all it depends on is kind of connectivity. We're going to see that's not the case for the second thing that we'll talk about. So here's our picture here. It took me a long time to converge on a reasonable picture that helps illustrate the difference between the different derivatives here. So here's a vector field. We're going to make this the x vector field. Okay, so here obviously I'm drawing the flow lines, and x is kind of squishing things as I move to the right. Okay, are you with me so far? Okay, so here's what we're going to define. We're going to define a particular object, integral curve, which is basically like the flow lines associated to a vector field. Okay, and those are going to be useful for defining the Lie derivative. For some reason in my notes I use phi, but I feel like that's redundant. Let's give it a new name. What Greek letter should I use here?
Psi.
Psi. Thank you. Creative. Okay, so yeah, let's define a flow curve. We'll call it psi t of p. Sorry, there's a bunch of indexing choices we can make. I'm going to change all of my notation for my notes just to make sure that I get it wrong. Okay, so we're going to define this object and call it an integral curve. And here's what it does. It takes a point P, and it takes a vector field x. It flows P along x for time t, and then it tells you where it went. Does that make sense? So in particular, it satisfies a particular ordinary differential equation. It's the following. Let's see if we can get it right. D over dt of phi t x p. Okay, so we know that it's like d over dt, but kind of a definition should be x, right? Yeah, acknowledgement, wake up. Yeah, okay. The question is, where do I evaluate x? This is where I always get it wrong. So like I'm a little car driving around on the surface. At time t, if I started at p, my location is this thing. And what should be my velocity? It should be my velocity evaluated at this point, right? So it should look like this. That makes sense? Okay. Did I get it right? I did get that right. Okay. So does everybody understand kind of what this object is? This is just this thing that takes your surface and maps it to itself, right? It kind of says like, where does every point go if I kind of scoot along the vector field for time t? Fun fact, this map is actually bijective for small t. This is a fact that we will not prove in this course. And maybe like is initially surprising because it kind of feels like you could cook up a vector field where things kind of move inward. But at least if you don't have a boundary, that can't happen. Yes?
When I took like differential equations class, there were these like weird cases where like there were two solutions where either you could just stay at zero or you could kind of stay at zero and then at some point like go off zero.
That's right. So in this class and in most of differential geometry, you just assume that doesn't happen. You put enough regularity on x that you have a unique solution to the ODE. Yeah.
Okay.
Mm-hmm. Any other technical points that I'm sweeping under the rug? I'm sure there are a few more. Okay, so right, so here's our vector field. So we wanted to define a derivative, and now we have all the ingredients that we need. It turns out, we can just build them all out of psi. So first of all, we need a way to take points and then move them along x a little bit. So conveniently, I mean, that's like precisely what this function psi is doing, right? So I might as well make a definition, gamma p of t is just equal to psi t to p, right? Because that clearly satisfies the conditions we need for A. Does that make sense? Kind of by definition, it does. In fact, it satisfies a little more, right? Like our definition A says that you only have to agree with x at time 0, but this thing says, in fact, just it's the thing that agrees with x for all time. Cool so far? Good? Yeah? Okay. Now we need B. We need some way to map tangent planes to each other. Yeah?
Right. So we're not supposed to have endpoints on curves, right? Like
We're not supposed to have endpoints on curves.
Open sense.
Yeah, so the reality is we're going to take a limit as t goes to 0, so the endpoint here really doesn't matter.
Okay.
Yeah.
Well, I guess I was worried about like the case where if x is ever 0, then you just like stop there.
That's fine.
Okay.
It's still a map, right?
Right. Yeah. I guess you would have an endpoint, but if you're taking smaller and smaller t's, then
You wouldn't have, like, a curve can, like, I haven't told you it's a regular curve. This isn't a curve like it's not something we're going to compute the curvature of. It's okay if it just stops. Yeah.
okay.
Like the whole field can be 0 if you want.
Okay.
In that case, talking about singularities doesn't make sense. There's other problems, but here it's okay. Okay, so we need a map from the tangent plane at P to the tangent plane at gamma of P, right? Or gamma P of T, rather. And conveniently, if you go back in our review slides, I guess I passed by them kind of quickly, but we actually had one. Namely, remember this is exactly what the differential of a map is, right? It's a thing that kind of can take vectors in one space and give me back vectors on the other. And yeah, okay? So in particular, since I have a self map assigned onto itself, I can take my function, my mechanism here, my phi p, to be equal to, yeah. Now you have to be a little bit careful how you do this. So phi maps one way, and if you look carefully at the differential of the map, you need to be careful what direction your map goes. So you end up with d psi, because this is a map of the surface onto itself, right? So d of that is a map of tangent planes. But remember that we want a map of the tangent plane at the target to the tangent plane of the source. So you kind of have to flip time backward. So it's actually d psi at minus t, p, I guess, evaluated at gamma p of t. So let's read this notation. So remember that d of a map gives us a map of tangent planes, right? Hopefully that makes sense. Remember what it does is kind of like draw a curve, you map it forward, and then you look at the image of the curve and kind of differentiate that object. So here, our mechanism takes the tangent plane at gamma t and puts it back here. But the problem is that this map psi does the opposite of that, right? It pushes you to gamma of t. And so that's where this minus t is coming from. And then this notation is just saying that I don't care about d psi generally, I just care about it at this one point. This is how to read this thing. Now, I see there. Now, this notion of derivative is quite easy to construct, like we just did. Ta-da! And the good news is that it uses machinery that we developed in this course, right? Like all I did was kind of munch together tools that we already had at our disposal. The problem is that this derivative acts really weird. We're going to see why in just a moment. Yes?
Nothing is weird.
Fantastic. So, in particular, here's the example, and I pinged a lot of friends to ask for good counterexamples, and I dug around a lot of geometry books, and this is missing. But this is the cleanest one. I asked it on Stack Exchange, and some anonymous person drew this picture, and they're absolutely right. This is the best picture. So, let's say that I draw a vector field, which is constant, so and points up, like that. And I look at the derivative along this straight line here. I think this is the simplest example to see the difference between our different derivatives of fields. Okay? Now, I think intuitively many of us would expect this derivative to be 0, but it's not actually when it comes to covariant, or when it comes to, oh god, I got it wrong. When it comes to Lie derivatives, it's actually not. And here's the reason why. This d psi object here is sort of accounting for this squish that happens along x. Right? So this derivative takes vectors here, and then when I pull them back here, it's going to stretch them back out with the field, right? Because it's kind of like the endpoints of this vector are moving apart as if I took the two endpoints of this thing kind of infinitesimally close to each other, and then pull them back, notice they kind of diverge. So from the notion of this definition here, this little pullback operation I have, right, this d psi, actually makes the vectors change, even if it looks constant. This is kind of like in physics when you talk about like non-inertial reference frames. Somehow there's like something very similar going on here. Like you have this weird reference frame x, which is stretching stuff out as I move along this axis. Because of that, the lens through which I compare vectors stretches it along with it. Okay, so this particular notion of derivative, in my mind, is actually quite counterintuitive. It like kind of doesn't behave the way you would expect a derivative to, but it does appear a lot. Like if you look in fluid mechanics, this tends to be the derivative that pops up in that domain. So in a lot of physics problems, this is actually the right notion of derivative to use. And the kind of interesting thing is it's purely topological. I actually don't need an inner product to define this thing. In fact, you can see that. Like we never used a dot product here, or like did a projection or anything like that. On the other hand, it's super counterintuitive, and the reason it's like similar philosophy to our Frenet frame. Like if I have very weak structure on my manifold, kind of the only reference I can get by just using the objects I have at my disposal and over again. Like the reference frame I have is just built out of X. Okay, so this object is the Lie derivative. You compute the flows of your field, you pull back vectors along the flows of the field, which could deform them in some kind of funny ways. Like here, you're like kind of stretching out this material as you move along this thing, and then you're comparing them. That makes sense? Do you notice, by the way, I see your hand. Like, do you notice how like this feels totally reasonable, but and moreover, it kind of like fills in our formula up here. But I would argue it probably doesn't lead to your first guess of what a derivative kind of should look like. And that's why I think it's so easy to get these definitions wrong. Like I think it's you have to be so careful trusting your intuition in this domain. Yes.
Where do we see that deep psi deforms the vectors?
Yeah. So here's there are many ways to view it. So remember how we define D here. Like you draw a little curve. You have to be a little careful. So like, let's say that I want the derivative here. So I remember I map forward and then I have to pull it back, right? So what would this do? This would take a curve along my vector field. So in this case, just a straight line like that, right? And then it would pull it back along the field, basically by tracing the flows by definition here, right? So what's going to happen to this curve as I pull it along the vector field? Well, now it becomes this much longer curve, right? So if we think about the velocity at this point was y, well here, it just got a lot bigger, right? Because the field is stretching out. So if you just think of like two infinitesimally close kind of endpoints, like this curve has a little displacement, they move apart as I move along this thing. And that's why even though it looks constant from our perspective, it's not from the x perspective because x is squashing the domain. Yeah, it's really hard to think about this thing. And it was just funny because like I think if I didn't draw you this picture and I just gave you this definition, you'd say like, oh yeah, that feels right. Yes, for sure.
It looks like this particular curve along which we take the derivative, it's some kind of equilibrium. So like, what if our vector field is pointing down instead of up? In that case, the derivative is going to be pointing up, right?
Oh no, are you going to make me just think about signs of things?
So it's like
let's see. So it gets taller. It's certainly true that
so like just continuing to it
No,
there.
it's getting. There's no discontinuity. So here the field y is pointing up even below the y-axis. It's just a constant. So there's no discontinuity. Like if I took y and flipped it, I'd have to pass through 0. So I think things are okay here.
You mean the derivative is continuous?
Yes.
Oh, wow.
Because y is just always up. It's up down here too. There's the x-axis here is a.
No, I mean like it's continuous with respect to the vector field. So like if y would be pointing up, the down instead of up. So like imagine we just rotate the vector field, and then I guess like at the point of when it's aligned with the curve, the derivative should jump from plus to minus.
You're right. Like probably when it goes horizontal, it might be 0 at this point. Yeah, that's certainly true. But then as it points up again, it'll become non-zero again. Yeah.
Continuously goes to 0, right?
Yeah. But yeah, if it's continuous, it just kind of changes. It just passes through 0. Yeah. So if you have like a rotating clock face worth of vector fields here, I think you'd be okay. I think I managed to make this picture totally terrible, but you know, we'll clean it up later. I'll point you to the stack exchange field. It's very clean. Yeah. Somebody even drew a picture for the stack exchange. It's very nice though. Right. Any other questions? Cool. So anyway, this is to me the cleanest way to visualize Lie derivative, and it is it's hard to think about. Like legitimately, I think these are just tricky. But this is I think the cleanest way to do it is to kind of understand what happens as the field is compressing stuff. Okay, so now we need a second desire, a second notion of derivative that maybe aligns a bit more with our intuition. Notice that there's also kind of a funny property of the Lie derivative, which is like, I want the Lie derivative of y along x. Clearly I needed all of x to compute the derivative, even if I only cared about its restriction along the line. This, I think, relates to our Chim question a little bit, right? Like, somehow I feel like when I differentiate, I shouldn't need x everywhere. Like, if I just wanted the horizontal derivative of my field, it shouldn't matter what's going on, like, vertically. But here, that's clearly not the case, because the vertical squash is affecting the derivative I computed, right? Yes?
So if we had just parallel transported y back, I think this would
That's a fantastic intuition. Like, well, the culprit here seems to be this thing, B, right? That like this machinery for transporting vectors, apparently, like it's multiplying by the Jacobian of x in effect, and that's causing some problem here. And conveniently for us, on homework 3, we defined a different notion of what it means to move vectors around, namely parallel transport. Parallel transport only needs a curve; it doesn't need x everywhere, right? So, conveniently for us, that is exactly the right question to ask, because that leads to a second notion of differentiating a vector field. Anybody know what it's called? I already said it like 5 times because I'm bad at saying the right word in this class. Close, covariant, but good listening. Okay, so is it okay if I erase this board so that we leave our 2 points above here? I guess I could use the board in the back, but that doesn't actually help us. Does anybody have a compelling use for the board in the back? I feel like you use it, then inevitably you're going to cover it up. Okay. Right. It's like a topological issue there. Okay. So, as our Chim brilliantly points out, we're going to have a second one. It's called covariant derivative. And this one is the one that kind of, I would argue, at least if you're a geometer, I guess if you're a physicist, maybe you think about Lie derivatives. I think in the geometry universe, this is the one that has sort of more intuitive behavior. So here's what we're going to do. Here, we're going to say that gamma p of t is any curve. C-U-R-V-E. Yeah. Satisfying the properties that we want. So, namely, just anything that starts at P and moves along our field X at time 0. It turns out, although this is, again, not something we're going to check in today's lecture because we're low on time, that anyone will give you the same behavior. It's actually not obvious from our definition. Okay. But Kirill points out that we have a reasonable way to move vectors around, which is not this funny pullback along the vector field flow. And that is parallel transport. So here's what we're going to do. We're going to say that phi TP is parallel transport along gamma p. And homework, I think it was homework 3, you guys worked quite a bit with this definition. If you recall, basically there was a little ODE that defined this thing, which was the following. It says that if I take the projection onto T gamma T P V of T prime, if this thing should equal 0. So in other words, like, let's see, I've got my curved surface. I draw my curve gamma like that. I set up an initial, so maybe here's the starting point, here's P. I grab my vector field, I guess Y, at the endpoint of gamma. Now endpoint is okay, we'll just do it at like epsilon over 2 or something. And now we're going to map it backward. And how are we going to do that? Well, we're going to say, maybe it starts at Y, and then it has this property that the rate of change of my vector never has a component in the tangent plane. Geometrically, do you guys have intuition for what this ODE is saying? I mean, you worked with it on your homework, so you're all experts. You're so quiet, but I know that you do. Yes?
I think it basically means that we're always kind of rotating the vector as we move along the surface.
It's actually sort of, I would argue, like a little bit the opposite of that. Like, in other words, like the component, like the vector is allowed to change, but only in the normal direction, right? It's not allowed to change tangentially, right? So in other words, like I'm kind of dragging my vector along the surface, and as I do that, I don't want it to just kind of spin arbitrarily, right? Like just like zipping around in the tangent plane. Somehow that feels unnecessary. I'd like it to just move as lazily as possible. A different way that fancy differential geometry people put it is that this is torsion-free. Like it's not inducing unnecessary twisting. Yes?
I would say we just only change that component such that it's flat. Right?
We only change, yeah, exactly. So essentially, we're the only edits we're allowed to make to our vector are ones that keep it in the plane. We don't do some extra ones that just kind of scoot around. Gotcha.
Isn't that the definition of parallel transport?
Yes, because that's what we're doing. Yeah.
Oh, yeah.
Nailed it. Any other questions? Yes.
Is it a problem that you can like parallel transport back to where you started, but not like be pointing in the same direction?
Yeah. So I'll ask you a question in a fancier way. Like, is holonomy an issue, right? There's this term holonomy, or in graphics for some reason holonomy. That if I take a vector and I transport it around a loop, I don't end up where I started. Remember in your homework you kind of argued that it has something to do with curvature? You might ask if that's an issue here. The answer is no, but it's a thing to check. In particular, the question you would have to ask is like, well, where could this come up? Like this definition feels valid. Essentially what we didn't check is that if I chose a different curve gamma, right, then it's certainly the case that the parallel transport for positive t would give me a different thing, right? Like if I had, here's my domain, and now I chose some other curve, even that if it had the same endpoint and the same initial tangent, it could be that like somehow covariant or rather parallel transport along these things just gives me something different. Like in an extreme case, maybe I'm just evil and I do this, along the path. But the reason why it ends up being okay, if you work through your calculation, is this limit. That like globally that could go wrong, but you're taking a limit as things go to zero, and then they all start to agree. Yeah, but it's a good question. That's good critical thinking. Yeah. Any other? So there's a lot of really nice properties to covariant differentiation. First of all, a property that in retrospect feels like obvious, but is not, doesn't actually work for the Lie derivative, is as follows. Let's say that so here the notation is typically we use the gradient like that. Oops, wait, did I do it right? Yeah, gradient grad x, y. By the way, the Lie derivative, typically we write L, x, y, like that. I'm going to erase so we don't confuse. So in order to compute that Lie derivative, I needed x as a vector field. I can't just say, like, give me the derivative of y at p in this direction. That's not a thing. I need the whole field of directions in order to evaluate it. It turns out it's perfectly fine to just evaluate this at p, only knowing the value of x at p. Right? If you look at this definition, notice that like if I know x at p, then I can do this whole thing. I don't need anything else, right? Which is one of these properties that, in retrospect, you probably want for your derivative, but a priori you don't have in this definition up here. Does that make sense? In fact, I believe if you add that property and maybe a product rule, then you can show this thing kind of has to be covariant derivative. I always get this wrong. Okay, so yeah. So now if we go back to our example, where we have these converging flow lines, like that, and now we have our vertical field here, right? Now life is good, right? Because if I parallel transport along this horizontal line in the plane, clearly my vector doesn't change, and I get zero derivative along this horizontal curve of my vertical field. Does that make sense? So there's order in the universe. By the way, one thing to notice here, like going back to this question about holonomy, like all of our weird counterexamples I've given you are on the plane. They're not actually on curved surfaces. Like these issues involving vector field differentiation already appear in flat geometry. It's not even like an issue with curved surfaces. Okay, so there's your whirlwind introduction to the two main derivatives that you encounter in differential geometry class. Any questions before we can go through some pictures on slides of what these things look like and kind of review the formula one more time? Yes?
If I think of taking a derivative of a gradient field,
Uh-huh.
I would think of like the Hessian. How
Mhm.
does this relate at all?
If you think of taking the derivative of a gradient field, for what, an exact field, a co-exact field, I always get it wrong. How do you get the Hessian? The answer, in short, is yes, right? But you have to be a little bit careful. So if you think of the columns of the Hessian, right? The column of the Hessian are kind of like the derivative of the x component and the y component of the gradient. Then you can get some notion out of these different derivatives. And as you can imagine, if I use Lie derivative or covariant, I'll get two different notions of Hessian. On your homework, you'll essentially take this covariant derivative notion and do it twice to get a Hessian-looking object, which makes some sense, but is really annoying. In general, Hessians are hard to work with in differential geometry for exactly this reason, which is that you kind of have to like define derivative. This thing outputs a vector field. You need to do it again, and so you have to be super careful. Like what does it even mean to write down a matrix anymore? It's like sort of you replace that with like a thing that inputs two vectors and outputs a scalar, right? Like an inner product. And defining that's a little annoying. In the theory of differential forms, your life is a lot easier. Then you can like take 2Ds and get something nice. Anyway, I'm mostly talking nonsense. If you open up the Wikipedia page and read like Hessian on curved domain, you'll see it's a messy discussion. Yeah. Yes, Leticia.
I guess I'm kind of confused by the fact that we start off from the same derivation and we arrive at two objects that obviously don't agree with each other, at
Mhm.
least on this example. Like,
You should be confused. This is one of these fantastic examples where I wrote down something that feels totally reasonable and then filled it in two different sets of details and got two completely different objects, right?
where do we reconcile those?
We don't. These are just two notions of derivatives.
They're
And
just useful in different
yeah, that's right. They're just useful in different places. So when you read through differential geometry books, depending on the calculation you're doing, you'll need one or the other. Like, so to put it differently, like we haven't actually used these derivatives for anything. We just define them abstractly, right? This is a good motivator for like, okay, if I'm going to do vector field processing, apparently I have to think about my application carefully. Because if I don't, then I can walk down all kinds of funny paths, making totally reasonable assumptions and ended up in different places. Yeah. Yes.
You said that Lie derivative is invariant to, so it's only topological, right? So
Purely topological.
if you deform the surface and it should stay the same. And I just like struggle to understand because like there are so many deformations and we can like choose deformations where we have a local distortion
Uh-huh.
and it will change obviously the fields
That's true.
and like
But the derivative doesn't change. No, you have to, when you say doesn't change, you have to say sort of modular that motion, right? So when you say the Lie derivative is invariant, you have to be careful that you have to map everything by the derivative by the Jacobian of the deformation you did to the surface, right? So like if I deform the surface, then I have to deform x, y, and the covariant derivative all by the same transformation, and then they all agree. Right, so you do have to account for the deformation. If nothing else, just because the tangent planes change, right? You got to do something. But yeah, up to that. It's a little surprising from this picture that should be the case, but it sort of makes sense in the sense that like all the Lie derivative is doing is just multiplying by assorted Jacobians of x and y in coordinates, and that somehow like that just doesn't depend on dot products. Yeah. But you're right, like there's a lot of things to check here. Like we're doing it quickly. Really, you should do that algebraically and make sure it's true. Yeah. Anyway, I think it's just mind-blowing and really hard to think about, which is cool. Like this like relatively simple notion of derivative is actually quite messy. So now let's fill in some pictures and this is basically just a review of what we already done on the board. But now that we've done it formally, we can kind of see some equations here. So first, if we want to talk about the Lie derivative again, the basic object that we have to define is this psi. Oh, Camila, I use psi here. What do you know? Which is this thing that flows along the field, right? So if I have vectors here, then of course these curves here are the flows. This is useful for a lot of different things. So for example, d psi, kind of go to our chance question, is like sort of accounting for the squish and stretch of the surface itself as it moves along the field, right? Like, so in this example, it's kind of like yanking things apart. There's one fun kind of special case, just incidentally, which is when this thing is the identity matrix, and then you get a special object called the Killing vector field. This is named after the mathematician Wilhelm Killing. It's not violent at all. Killing vector fields are very special objects. The next time you're in the bathroom, you can observe probably the only example you'll see in your everyday life, which is if you take your toilet paper roll and you spin it around its axis, and you kind of look infinitesimally at the motion of the surface along itself, then notice that that thing is preserving the metric of the surface as it goes around. Right? So that's the example, the kind of calculation you can do just working with d psi. More generally, of course, we have this notion of differential, which kind of flows things along curves. And that leads us, or led us, to our notion of a Lie derivative. Here's slightly different notation for the same thing, but now we kind of get what's going on. Where, again, you're just accounting for the squish and stretch of one field along the other. But in this case, because you're using vector field flows, the structure of V away from its flow lines matters, right? Like the flow lines are going apart, then that gets accounted for in the field structure. And most importantly, it is Lie derivative and Euler. Okay, and here's our handy picture from this kind gentleman on Stack Exchange to kind of explain the difference. That, like, you know, from perspective of covariant derivative, you know, my blue vector field as I move it along here doesn't change, whereas from perspective of the Lie derivative, it kind of looks like the red field is like stretching along with the field, and that's why when you compare them at the same base point, you get something different. Yeah. Okay. Incidentally, this guy turned out to be super cool. He was emailing me thoughts about our research and had all kinds of interesting ideas. So the internet is great. Okay, and so right. So because of this kind of weird behavior of the Lie derivative, essentially, if we go back to the drawing board and said well, what if we just wanted the derivative of the orange field in the blue direction? Notice this is not enough information to compute Lie derivative because I would need the blue field in a little patch around this point. That led us to using parallel transport, right? This nice identification of different tangent planes, which you did in the last homework. And for our final trick, this leads us to this nice formula for covariant differentiation, where essentially all I have to do is, at least in 3D, where I'm allowed to have vectors, I'm allowed to do subtraction outside of the plane. Of course, in Riemannian geometry, you will not see this formula because there exists nothing outside of the tangent plane. But here we can. So it turns out it's actually quite simple. You just take the field along your curve, and you compute the derivative in t, which is some vector that probably has a component normal to the surface, right? Like if the tangent plane is changing. So you just project that out. So in some sense, if I asked you all to compute the derivative of a vector field on a surface, and told you it had to be tangent, this is probably what you do, right? You compute the derivative in a direction and then just project out the normal part, and it turns out you would be right. But it does take a lot of work to check that this is a reasonable definition. Okay. Yes.
And only accurate also if it's very small, right? If it doesn't-
Only accurate if it's small.
Like you lose if you discretize not well enough, you lose part of the vector.
Oh, we've not talked about discretization at all, right? So in particular, how do you discretize parallel transport is a tricky matter, right? Yeah, because here, this little prime is doing a lot of work. And we don't have access to that prime on a triangle mesh, right? Because there's a thing that happens in between triangle planes. And so we have to account for that. Yes?
Is there a sense in which we could think of this as aligning the tangent planes by making the principal curvature directions line up?
No.
Okay.
No, but principal curvature directions, no. But you could think about it. So actually, the discrete version we'll see of covariant differentiation is even cleaner. It's you have two triangles that share an edge. You kind of hinge that edge to be flat, and then you can just displace vectors and then put it back. So that's the right way to think about it, is that you're hinging about a shared edge. In general, no, because again, remember covariant derivative is intrinsic, so we know anything involving principal directions is wrong, right? Because we can't measure those if all we can do is intrinsic geometry. Yeah. So it's an interesting intuition, but not quite there. Yeah. Any other questions? Yes.
So, and it shows that the derivative on this edge of the star is going to be undefined.
Oh yeah, this is actually probably a bad picture. This is we have not talked about how to differentiate things along sharp edges. Yeah, so far in the theory we've written down it would be undefined. I think you could actually, if you really wanted to extend to this case where you have a boundary but it's smooth, I think you could. Question mark. And the way that I would do it would be actually to borrow from our next lecture, where we're going to talk about triangles, so everything there looks like this edge. And I believe you could basically do it by taking a curve that hits the corner here, and then having it continue around the other edge of the corner, and then kind of hinging about that, just the same way that you have a triangle. But I'd have to think about it. It's a good question. You're right, this is not a great picture. Yeah. Okay, covariant derivatives are cool. I have a t-shirt that says that. And they satisfy all kinds of nice properties. For example, they're linear in the lower slot and on the upper slot in slightly different ways. There's some notion of a product rule. You can relate it to the Lie derivative through this torsion-free property. This property turns out to be sort of the one that makes covariant differentiation unique. If you don't have it, like so if you start from a modern differential geometry book, they will forget all these pictures here, and they'll say, I want a thing that inputs two vector fields that satisfies these 5 properties. And they'll show that it has to be unique. Does anybody have any idea what this thing is called? If you kind of take that approach. It's a very famous name. This is the Levi-Civita connection. Or it was actually Levi-Civita connection. I had my undergrad differential geometry professor apparently thought he was Italian, and that was not right. Or if it was, then it still was pronounced wrong. But in any event, yeah. So you can sort of axiomatize this picture, which is nice. Again, if your goal in life is to get rid of pictures and do all of geometry in symbols, and so that's what happens here. It turns out there's a lot of derivatives that satisfy properties 1 through 4, and then this thing is enough to make it unique. Yeah. Okay. I will let you think about this at home. There's like a nice little problem in this Lie textbook to help kind of challenge your understanding of Lie derivatives versus covariant derivatives. I've listed in the slide, and you should think about it on your own. Okay, so to kind of wrap things up just a tiny bit for today, it turns out a lot of the things we've done in this course are very cleanly expressed in terms of this object we've just defined. So for example, remember we talked about geodesic curves as satisfying this condition here, that like they kind of don't change the steering wheel. This is a long time ago now. Feels like months, because it was. But now notice, like, what is the projection onto the tangent plane of the derivative of something? Well, we just defined that to be a covariant derivative. So in fact, here's a much cleaner expression for the same ODE, which is that a geodesic curve is one where if you take the derivative of the curve, and now you take its covariant derivative in its own direction, you get 0. Right? This is just cleaner notation for what was on the previous slide. Similarly, if I wanted to find parallel transport, I can do so using the same notation, right? Because this is like saying I have a vector field V, where if I move along the curve and I take the derivative, like the covariant part, which remember is just derivative projected back on the plane, then I should get 0. These should be interesting hints to you guys that this delta object is really fundamental, right? And so again, in modern differential geometry, you usually start by defining this object. And then you go back and you say, well, what is a geodesic curve? Well, I'm just going to define it to be a thing that satisfies this property, right? And the reason to do that is now it's much easier to make sure your theorems are right, right? Because now suddenly you have all these pieces that are all kind of built on one operating system, which is your connection. And then similarly, we talked about some other notions. Very briefly, here's a picture that I guess we won't get to today because we're low on time. There's an important consideration when it comes to vector fields, which is their topology. So far we talked about the geometry of vector fields, right? Like how to compare vectors to each other. But you might also talk about the global structure, and there's some really beautiful theory here. So typically on 2D surfaces, here's where we transition from manifolds to 2D. Like everything we've done so far is fine in high dimension. On 2D surfaces, we can look specifically at points, at least when they're isolated, where a vector field is 0, right? And then we can make a really interesting construction where you just draw like a little loop around that point, and you look at the direction of the vector field, right? So here, just the direction. We're not concerned with the norm, other than that it's non-zero, because again, we're going to assume these points are isolated. Okay. So you think about it, it's kind of like a little clock face, right? Like if I take the surface and I kind of unwrap it to be flat locally. So I've got this vector field which kind of points in different directions. And there's a reasonable question you can ask, which is as I circulate around my point, how many times does that clock rotate about its face? Right? So for example, if my field just like points to the right, the answer is 0. Whereas like in this radial field, you can see it's degree 1, right? Like as I go around the face, obviously this direction takes a full degree. So this number, the number of times I rotate, is called the degree of a singularity. Yes?
It has to be an integer, right?
Has to be an integer, right? Because if I go around the loop, I am back where I started. Yeah. So there's a beautiful, beautiful theorem in differential geometry involving the index of a singularity. This is called the Poincare-Hopf theorem, or in my textbook, it was the Hopf-Poincare theorem, which essentially says if you take all the singular points of a vector field with isolated singularities, meaning that it can't be 0 like on a patch or like in a path, it has to be 0 in isolated places, and I add up all the indices, I get the Euler characteristic. This weird object is somehow unescapable. So this is a really beautiful little theorem. We'll see that there's discrete versions of it on triangle meshes, which is very clean. Does anybody know a very famous corollary of this theorem? It's a close one, so it's a very sore topic for me.
The Hairy-Ball theorem.
Yeah, the Hairy-Ball theorem, which says the following: if I take a sphere or a ball and I cover it in little hairs, like a vector field, it's tangent. Well, necessarily, if you think about it, like this thing has got to have singular points that add up to the Euler characteristic, which is non-zero. So in particular, there's at least one point which is singular, right? Because otherwise you wouldn't have 0 index, yeah? And so in this theorem, essentially what it says is if I take a ball and I cover it in little tangent vectors, somewhere it has to vanish, right? So there are lots of interesting corollaries of this. For instance, like if I look at the weather patterns on the Earth, which is roughly a sphere, right? Then I look at all the wind, right? So wind is a vector field. One could argue whether it's a regular vector field or not, but we're not going to get caught up in the details. Somewhere at every point in time, there is some point on the Earth where there is no wind, right? That's the sort of corollary of the Hopf-Poincare theorem, or like whatever this bizarre diagram is from this textbook from the 1970s. Right. To move forward a tiny bit, if we extend, and maybe actually we'll leave this for next time, we'll talk the tiniest bit about how to represent this slightly more generic object called a direction field, where at every point, like for example, with that quad meshing example we saw at the beginning of class, I don't just need one direction at every point, I need like 4, right? And so actually, here's what we're going to do. We'll end on time for once, and for our next lecture, we'll start here, and I want you guys to think about, like, how would I represent this object? In particular, I have 4 vectors at a point, and it's an unordered list, right? So I don't care, like, I don't want this to be vector 1, 2, 3, 4. I just want there to be 4 things. How could I represent that object mathematically is a good, tricky question to ponder. Yeah, so we won't go to the next slide. Next time we'll start here. We'll talk about how to represent direction fields, and then we'll talk about field discretization. Does that sound good? I think it sounds good. So have a lovely whatever, and I will see you whenever. Okay. Right, so now I've got to stop recording and stop this thing, right? 1, 2, 3.